Okay, let's continue our chapter for gravitation. So let me draw a circle. So this one, okay. So this one will be our Earth, which is a sphere. Okay, so let's say we have an object here, which is mass m. So this mass is moving towards the direction of the Earth. So as we know that when the attraction between Earth and the object with mass m is the force between them is always gravitational force, which is negative gmm over r square. So this from the center of the Earth, the distance from the center of the Earth until mass here is a distance x. We denote this as distance x, or r also acceptable. So as we know that as this object is moving closer and closer to the Earth, so the change in the distance is always negative dx. D means delta, which is change. As the distance is keep decreasing, and so we denote this direction is as negative, which is directed toward the center of the Earth. Okay, from here we can know that okay, let me erase all this one. Okay, right. Okay, as we know that gravitational force is always negative g mm over r square. Okay, there is an energy between the Earth and the mass m. The energy which the energy, or we call it work done. Work done for the Earth to move this object from A to B. So this one will be denoted as B. So work done to move from A to B is what we call gravitational potential energy. Potential energy. Okay, so we are going to derive the gravitational potential energy from this gravitational force. Okay, so gravitational potential energy, which the symbol denoted as U. So U basically is actually the integration from from infinity, which is the point which is any point, or we can say an unknown point, to a distance which is called r. So so this one will be our g mm over x square. We should write x square. Okay, so to be more easier to be understand. Okay, so this dx is always opposing to the increasing r. So this one will also negative, since the gravitational force has the negative, which is always opposite to the increasing r. Opposite to the increasing r. So this one, so gravitational force is negative, So this one del x is also negative, which is the distance is keep decreasing and more closer to the Earth. Okay, so negative will eventually give us positive. So this one is r infinity. So gmm over x squared. So let me erase this one. Alright, from here to here. Okay, let me. So here. Alright, so this one, we can see that from between r and the infinity point, so the infinity point should be bigger. So based on mathematics theory, we must convert this infinity to upper part and the radius to be lower part, which means that this r, not radius, this r should be smaller and this infinity point should be bigger. So based on mathematics formula, we know that if we convert these two values, so eventually we will get negative. So this one will be infinity and this one will be r. So okay, gmm over x squared del x. Okay, so we integrate this one, we will get negative gmm over x. Okay, which is infinity and r. So we know that, okay, we know that if x is approaching infinity as for reciprocal, which is reciprocal 1 over x, so actually the reciprocal graph will approximately get 0. So this eventually, for if x is at infinity, so the gravitational potential energy will eventually get 0. So this one will be our gmm over r. So the final answer what we got will be actually negative gmm over r. So this is our gravitational potential energy. Alright, so let me erase this one. Okay. So what is the definition for gravitational potential energy? So U, I write in the expressway, which is U for the symbol of gravitational potential energy, is actually defined as the work done to move a mass the work done to move a mass from infinity to a point. So this is how we explain the definition for gravitational potential energy. Okay, so let's move to the next part. So what is actually is the meaning for gravitational potential. Gravitational potential. So the gravitational potential, which is denoted as phi, is actually defined as the work done, also work done, which same as gravitational potential energy, work done to move. So this will be our keywords: to move a unit mass from infinity to a point. So this unit mass means 1 kg, which means that gravitational potential is the work done to move 1 kg of the object from infinity to a point. So the U here is to move a mass. Okay, so this a mass means the total mass for the object. So this a unit mass means 1 kg of the object from infinity to a point. So which means that our gravitational potential energy, which is U, is actually equals to our V, which is gravitational potential, divided by M. So our V is actually equals to UM. So gravitational potential energy multiplied by the mass of our object. So this is how we determine the gravitational potential, okay, in terms of qualitatively and quantitatively. Okay, there's another quantitative answer for gravitational potential, so let me show you that. Okay, so let me erase this one. So in terms of quantitative explanation, so okay, so actually gravitational potential, okay, let me explain first. Okay, so this we know that acceleration due to gravity, or we can say that gravitational field strength, is actually equals to negative gn over x squared. We write it as x. Okay, this negative is we know that is opposite direction to the increasing r. So our gravitational potential is actually equals to the integration, which is from infinity to r. So this one will be our negative. So gm over x squared. So change in x, which is closer and closer to the direction to the earth, which is towards the direction of the earth. Okay, so the change in x will be negative, same as how we integrate the gravitational force. So this will be positive, okay, gn over x squared dx. So same as just now, we know that this infinity is bigger than r, so this one will eventually give us negative. So this one will be our infinity r gm over x squared dx. So we integrate, we will get negative gn over x, so infinity r. So for reciprocal graph, we know that if 1 over x is approaching infinity, it will eventually give us 0. approximately 0, not totally 0, okay? So negative 0 minus negative gm over r. So this one will give us negative gm over r, which is our gravitational potential. So we can conclude that our gravitational potential, gravitational acceleration, or we said that gravitational field strength is actually equals to our dv dr. So this one will be our negative. So this is how we explain the gravitational potential in terms of quantitative way. So okay, so let me erase this one and remove this one as well. Alright, okay, so what is the variation between V and R? So we know that V actually equals to our Gm over R, so this one will be our negative. Okay, in terms of graph, so let me draw a line. So this one will be our V, so this one will be our R. So here, same as from the previous graph, we have inside the earth and outside the earth. So here, so this one is Gm over R, which is negative. Okay, inside the earth, our gravitational potential is always the same. As for outside the earth, we know that V is inversely proportional to the distance between the earth and the object. So what we got for this graph is actually reciprocal graph. So this is how we represent the relationship between gravitational potential and the distance between two objects in terms of graph. Alright, so we have done for the gravitational potential. So let's move to the next parts. Okay, so let's discuss about satellite in circular orbit. Circular orbit. Okay, so let me draw a circle. So this will be our Earth. So let me draw another circle here. So let me see whether can I. Okay, so here. Oops. This one should be the ellipse, not the perfect circle. So let me draw another circle here. I try my best to draw it as perfect as I can. Alright, this would be better. Okay. Okay, so this is actually the radius of the Earth. So this is the distance between the center of the Earth and the satellite. Okay, So this one will be our radius of the Earth, which is capital letter R. So this one will be our distance between the center of the Earth and the satellite. So this will be our small r. Alright. Consider there's satellite here. So this satellite is about to revolve the Earth. Okay. Oops. So this satellite is about to revolve the Earth. Okay. So which is the linear with the linear speed v. So we know that the satellite will be, how should I say that, the satellite will revolve the Earth. So as the satellite is revolving with the certain velocity, okay, let me write here, satellite revolving with certain velocity, so there exists a how should I say, okay, revolving with certain velocity, and so this is the first point. So the second point is the force, the only force acting on the satellites, we know that is always gravitational force. Gravitational force. Okay, so as the gravitational force acting on the satellite, suppose the satellite is moving down to the center of the Earth, which means that the satellite is about to fall and drop into the atmosphere of the Earth. Suppose it should be like that, but with the certain velocity here, as the satellite moves with the certain velocity, and this causes the satellite to revolve around the Earth, so this gravitational force will eventually equals to our centripetal force. So this which means that the gravitational force which acting on the satellites is used to be centripetal force which moving, or we can say that is orbiting around the Earth. So this is how satellites orbiting the Earth with these forces, not forces, should be one force. This is because gravitational force is actually equals to our centripetal force. So how can we find the specific velocity for the satellite so that it moves with that velocities and do not drop into the atmosphere of the Earth? So based on this equation, we can know that. So this one will cancel each other. So this one will be cancel, and this one will be our R. So this one will be gm over R, which is v square. Okay, so v is actually square root of gm over R. So okay, alright. So as we know that not only the gravitational force acting on these satellites, we also have the gravitational field strength. Gravitational field strength, strength, which is G. So the gravitational field strength, or we can say that gravitational due to gravity of the Earth, is also acting on the satellites. So we know that G is actually Gm over r square. So um, so when we move this r square to the G side, so we will get gr square. So eventually Gm we sub into here, so Gm, which is gr square over r. The final answer we got for our velocity is actually such gr. So this can be our final answer, or this one as well. So this two formula is actually important for us. So let's move to the next part. Alright. So let me erase this one. So this one as well. Alright, let's talk about synchronous satellites. Synchronous satellites. So what is actually means the synchronous satellites? It means that, okay, it means that we know that okay, we know that satellite is always orbiting the Earth Okay, so as we discussed just now, satellite undergo circular motion by through the gravitational force. So the gravitational force able it to orbit the Earth. Okay, so these synchronous satellites, it means that the satellites orbiting the Earth which the period of revolution which is capital letter T, which is for one complete circle, as we discussed from the previous chapter. Okay, so one complete period of revolution for one complete circle is equal, which the period of revolution is equal to the period of revolution of the Earth. Alright, this is the meaning for the synchronous satellites. Okay, we know that the period of revolution of the Earth in one day is actually 24 hours. So this satellite is about to revolve for 24 hours, which is same to the previous period of revolution of the Earth. So this is what we call synchronous satellites. Okay. So okay, let me so actually we can find that what is the distance between the center of the Earth until the satellites, so that the synchronous satellite can be occur. So we can find that the distance between the center of the Earth and the satellites. So we can find through this formula, which is mr omega square is equal to gmm over r square. As I told from the previous video, by saying that the negative is not necessary to be written in calculation, as it only represent the direction for the gravitational force. Okay, so this one will be our r cube. So this one will be cancelled. So this one will be 2 pi over t square. So this one will be gm. So gm t over 2 pi square r cube. Okay, so we know that oops, I should write in terms of, okay, for the gravitational constants is oops, okay, let me, okay, from gm, we know that gm is actually equals to gr square. So this one will be t square over 4 pi square. So g is actually 9.81. So radius will be 6.4 times 10 to the power of 6 square. So the period of revolution for the Earth is actually 24 hours times 60 minutes times 60 seconds over 2 pi. This is our square. So the radius we got for the final answer is actually 4.24 times 10 to the power of power of 7. So at this distance, only at this distance, synchronous satellite will be for the, how should I say, only at this distance synchronous satellite is able to occur. Okay, so let me erase this one. Okay, let's talk and let's proceed to the next part. Okay, from this formula, we know that mr omega square is equal to the gravitational force. So we cancel each other and simplify it until we get this one. So this formula, we can see the variation between the radius and the period of revolution, which is not radius okay, which is this one will be our distance between two planet or one planet and one object or whatever. Okay, r cube is actually directly proportional to the period of revolution. So what is this means? Okay, let me show you. Okay, so this is our sun. So this is our, oops, okay, let me draw another circle. Okay, this better. Alright, so assume that we have our sun here. This is our solar system. Okay, we know that our Earth or other planet, I did not draw all, So this one will be our Earth. We know that our Earth is always orbiting our Sun, so with linear speed v and angular velocity also, which is omega. So we know that our Earth is always orbiting the Sun for 1 year, which is 365 days. So this means that the distance from the center of the Sun to the Earth, so this one will be our centripetal force. Okay, so our Earth orbiting the Sun for 1 year is actually 365 days. So this shows the relation for the distance between the Sun and other planet besides Earth, not besides Earth, include Earth. So the distance between Sun and other planets is actually directly proportional to the square of period of the other planets. So let me write down so that we can see it clearly. So how to represent it in terms of sentence? Okay, let me write it here. Okay, from this relation we know that the cube of distance between Sun and okay, let me think how to the cube of the distance between the Sun and the planets revolving it is directly proportional to the square of period of revolution. To the square of period of revolution of the planet. So okay, so this one will be our explanation, and this will finally give us a law which is called Kepler's third law. Let me check the Kepler's. Okay, yeah. So Kepler's third law actually states that the cube of distance between the Sun and the planets revolving it is always directly proportional to the square of periods of revolution of the planets. So this is how Kepler's third law explain the revolution of the planets to the Sun in our solar system. So okay, let me erase this one. So this one as well. Alright, from this equation which is t square is directly proportional to r cubes. So it means that the um, the larger the radius, which is the bigger the size of the planets, okay, the longer is the period of revolution for the planets. Okay, let me give an example. Okay, let me give an example. So let's say Earth, we know that the radius of the Earth is actually given as 6.4 times 10. Oh, I'm sorry, I forgot. So the radius, okay, I forgot the radius of the Earth. So, okay, we know that the radius of the Jupiter is always bigger than the radius of the Earth. So the larger the radius is, so the larger is the period of revolution. So this is that is why we know that the period of revolution for the Earth is actually 365 days for one complete circle after revolving the Sun. As for Jupiter, for one complete circle, if it is about to orbit for one complete circle of the Sun, so it needs for 12 years to complete one circle. So this is how we explain the Kepler's third law. Okay, so let me erase this one and let us proceed to the next part. Alright, so let me see what's next. Okay, let's move to the energy of the satellites. Okay, we know that as we discussed just now about the gravitational potential energy, so this one is represented as U. So U is actually equals to negative GMM over R. So that when the satellites, okay, this is our satellites. So this is our Earth. So this is the circle which orbits the satellites. Okay, so we know that how should I say that? Okay, so since satellites revolve the Earth and the gravitational force is only force acting on the satellites, okay, so we know that mv square is equal to r. So not equal to r divided by r is actually equals to g mm over r square. So this sorry, where should I, okay, we did not cancel it. So we move this r to another side, so we eventually will get gmm over r. So as the satellites revolving the Earth, we know that there's another energy which is kinetic energy. Sorry, should be K. Kinetic energy. So there's kinetic energy and potential energy acting on the satellites. Okay, so kinetic energy is actually equals to half mv square. So this half mv square, okay, from this formula, mv square is actually given as gmm over r. So what we got is half gmm over r. Alright, so our total energy, we know that total energy is actually given as U plus K. So U plus K, which is negative gmm over R plus gmm over 2R. Oh, there's a note here by saying that for this negative, in terms of gravitational potential energy, is necessary to be written in calculation. Okay, so negative is important in calculation. So this negative gmm over r plus gmm over 2r eventually will give us negative gmm over 2r. So this is how we find our total energy of the satellites. Okay, so let me erase this one. So in terms of graph, okay, in terms of graph, let me draw a graph here. So this one will be our energy. So this one will be our R. Alright. So let me draw it longer. Okay, we know that for kinetic energy, so which is K, is actually equals to gmm over 2r. Okay, so our kinetic energy is actually at the positive parts. So this one will be reciprocal graph. Okay, as for total energy, which is gmm over 2r, and negative is included, and for our gravitational potential energy, gmm over r. So our negative gmm over r is actually so this one will be our gmm over r, which is also reciprocal graph, and at negative side, which because we have negative in this formula. So okay, so okay, let me label it. So this one will be our U. So this one finally will be our total energy. So this is how we represent these three energies in terms of graph. Okay, so we have done for energy. So let's move to the next part. So let's proceed to weightlessness. So what is weightlessness? All of us know that weightlessness is actually we can't feel we can't feel our weight, which is mg, anymore when we are we are on the outer space. Okay, we are in the outer space, sorry. So okay, when how can weightlessness occur? So weightlessness is occur when centripetal acceleration is equal to the acceleration due to gravity. So this is our gravitational acceleration. So our gravitational acceleration or acceleration due to gravity is actually equals to our centripetal acceleration. Okay, as I mentioned just now, for the satellites which is revolving the Earth, so our gravitational force, suppose we are about to drop into the atmosphere of the Earth and drop back into the center of the Earth, but our gravitational force is converted totally into our centripetal force, which with our certain velocity, which is v. So this causes we are not able, not to say not able. So we are able to stay in these orbits and do not fall into this atmosphere. So this, okay, so let me erase this one. This is not related, just for the example. So weightlessness is when our weight, okay, so how to write? So let's say an astronaut, this is our Earth, and this is our astronaut. So this is our astronaut, and let's say this astronaut is about to orbit this Earth, our Earth. So actually, when the astronaut is about to orbiting our Earth, so his weight is actually converted to the centripetal force, same as the satellites, as I explained just now. So this weight is actually totally converted to the centripetal force. Alright, so the centripetal force is actually equals to our gravitational force as well. Alright, this is how we explain the weightlessness. Okay, so alright, that's it for weightlessness. Okay, let me explain it in terms of qualitative explanation. So the first point, weightlessness occur when centripetal acceleration is equal to acceleration due to gravity. As for the second point, okay, so acceleration due to gravity, since acceleration due to gravity is equal to our centripetal acceleration. So alright, so it means that when gravitational due to acceleration is converted to centripetal acceleration, so it means that our weight, okay, or should I say our gravitational force is equal and considered as centripetal acceleration, centripetal force, okay, centripetal force. Hence the satellite will undergo circular motion, and hence we will able to stay in this orbits instead of falling down into the center of the earth. So this is how we explain the weightlessness. Since our weight is converted into centripetal force, so we lost our weight and we will feel weightless at the outer space. Okay, so this is how we explain the weightlessness. So we have done for this part. So okay, let me erase this one. Okay, let's move to the last part, which is explaining about the escape velocity. Escape velocity. Okay, so what is actually meant by the escape velocity? So escape velocity is actually defined as the minimum velocity required okay, velocity is required to move from the surface of the earth, and free from the gravitational pull. This is how we explain the escape velocity. Okay, so how can we derive the escape velocity of an object? Okay, so let me erase this one. Okay, we know that the total energy, as we discussed from the previous part, the total energy is actually equals to our gravitational potential energy plus the kinetic energy. So this one will be our GMM over R, so plus G half mv square. So this is our total energy, just for the reminder. Okay, so let me draw. Consider we have a rocket here. So this rocket is about to move against the gravitational pull until the infinity point at the outer space. So based on principle of conservation of energy, of conservation of energy, okay, it's by saying that the total energy before is actually equals to the total energy after leave the earth. Okay, so this one will be our total energy before leaving the earth is equal to our total energy after leaving the earth. Okay, so this is our GMM over R plus half mv square. So this will be also, okay, so this one will be our u, which is the initial velocity. So this one will be our R1. Okay, so this is what we are focused on, which is the escape velocity. Okay, so this one will be our GMM over R2, so plus half mv square. So let me erase this one. This one as well. Okay. Alright. So what we focus is the initial velocity, which is the escape velocity before leaving the earth. So this velocity is not necessary to be found, so we can convert it to GMM over 2R. Okay, so the total energy after leaving the earth, okay, is actually given as negative GMM over 2R. Okay, so this one will be as usual R1 plus half mu squared. Okay, u. So as 1 over r approaching infinity, what we got is actually approximately equals to 0. So this one will give us 0. Negative GMM over R1 plus half mv square. Okay, so let me erase this one. So this one as well. Okay, we are about to derive this initial velocity, or well known as escape velocity. So this one will be half mu square, or you can write as v is also acceptable. I write as u so that you can remember, you can understand more easily, as this one will be our initial velocity before leaving the earth. Okay, so this one will be our GMM over R1. So this one will be cancelled out. 2GM over R1. Okay, u square. So u is actually 2GM over R1. So GM, we know that GM is R square G. So R1 square G. Okay, this R is also the initial distance between the okay, how should I say, between the rockets and the earth. Okay, so this one will be our R1. Alright, So this one will be 2gr. Not the initial distance between rockets, and this r is actually given as the radius of the Earth. So this one will be our capital letter R. This one is the radius of the Earth. By saying that the gravitational potential energy is actually for the Earth, okay, which adds on the rockets, of course. So this one will be our R. So this distance is no more the radius of the Earth, is the distance which is at the infinity. Okay, I hope you can see, you can understand clearly. Okay, so our final answer for the escape velocity, which is equal to u, is actually sub2gr. So this is how we explain and how we can find the value for the escape velocity. Okay, so this is the last part for our chapter. So I hope you can understand more further after watching this video. Okay, I'll see you in the next video. Okay.